So in 5.2, we're going to talk about what we call definite integrals. Okay, so this is a term that we're going to be introduced to today. It's Riemann sums. Riemann was a mathematician, so it's named after him. So what we learned until now is how to estimate the area under a curve, basically, right? And so we were estimating distances, areas, and so on. And what we were doing is we were using finite sums. So what does it mean, finite sums? We have here, okay, so you know what infinite means. Finite is the opposite of that. It's basically something that you can count, okay, that is defined. So here we have a sum of a finite number of things, right? We have, like we were having 4 rectangles or 6 rectangles. These are, you know, and this is an amount that you can count. So that's a finite amount, okay? So now we're gonna move beyond these finite sums, because at the end of the day, even if you have 1,000,000 rectangles, that's still a finite number, and it's still a sort of an approximation. It's not good enough. So we're going to move beyond the finite sums to see what happens when you take a limit as those approach infinity. All right. So in that limit, okay, so when I have, you know, like something like this, when I have 4 rectangles, the length here, the width of each one is a half, right? So when I have 8, this gets smaller. When I have 16, they get smaller. Well, when I have an infinite number of rectangles, how wide is each one? Almost, what happens? Does it get bigger or smaller? Almost 0. Smaller and smaller and smaller until it's almost 0, right? If I have like an infinite number of these here, each rectangle has a length of almost 0. So as we're going to do that, the terms will become infinitely small and their number will become infinitely large. So I can, you know, list the numbers that I'm adding up like this, or I can write it as a sigma in sigma notation. Okay, so this symbol here, this is the Greek letter S. So in the Greek alphabet, the letter that gives you that S sound, just like our English version S, in Greek, it's sigma. That's what it looks like in the capital. And then lowercase sigma is this, okay? All right, so sigma, that symbol is used for sum, okay? So this is what sigma notation looks like. So here we have sigma, the sum of a sub k, and then k goes from 1 to n. Basically what this means is k is like a counter, like number 1, number 2, first term, second term, third term. So you keep putting them in. So a sub 1, whatever it is, you add it to a sub 2 and a sub 3 until you get a sub n. So that's what sigma notation is. Now, what we did yesterday and the day before, LRAM, MRAM, and all that stuff, these are all examples of Riemann sums. Okay, now let's talk about this theorem for a minute. It says the existence of definite integrals. This process is going to lead us to what we call an integral. Okay, so this says all continuous functions are integrable. That means if a function f is continuous on AB, closed interval AB, then its definite integral exists. Okay, if this doesn't mean that much to you right now, you're good. It shouldn't. All right, later on it will. Okay, now the definite integral. Okay, so let's talk about what a definite integral is. If f is continuous on AB, okay, and suppose you partition AB into n subintervals of equal length. All right, so here we're going from A to B. Here's some function. We're going to split it up into n subintervals, n rectangles. What's the length of each rectangle? Basically, you do b minus a divided by n, right? Does that make sense? So if we're going from 3 to 7, and you want 4 subintervals inside, how do you know how wide each one is? 7 minus 3 over 4, right? So that's b minus a over n, okay? So this length, now we're going to call it delta x. You've seen that in physics before. Delta x, it's basically the change in x. How much did x change in going from here to here? So delta x is b minus a over n. Okay, now, what is this thing definite integral I'm talking about? What is that? Well, definite integral means this. Okay? Definite integral a over b is the sum of, okay, f, the value at each x point times delta x. Okay, so what does that mean? If I take this one, okay, if I do f of 3 times however wide that is, what does that give me? If I do f of 3, which is that height, times that length, what does that give me? Huh? The area, right? So that's the area of that red one only. Now, if I add up all of them, that gives me the area under the whole curve. Is that right? And that is a definite integral. Okay? Huh? It just keeps going and going and going. All right, so let's think about what this is. So this f of c is the height, delta x is the length, and then you add them all up. So what we got here is the area under the curve with rectangles. Okay? Now, this is a cute little notation, but it's too crowded. So Leibniz introduced a different notation for the definite integral. He said, you know what, I'm not going to write it this way. This is like too many symbols. He introduced a different notation, and this is his notation. Okay? So this is the integral sign. Guess where it comes from? Lots of people don't know this. What letter is this? S. And then if you squish it and like stretch it, that's like a squished, stretched S almost, right? Because like this is the Greek S, and then he used like the Latin S. So basically it's the integral, the sum of f of x. What was f of x? It was the height, right? So this is the height. Instead of delta x, okay, so here it is. What's the Greek alphabet? It sounds like the Hebrew alphabet. The Greek alphabet is alpha, beta, then there is gamma, then the fourth one is delta, right? So A, B, C, D, okay? Delta, the fourth letter is this. It gives you the D sound, okay? So rather than having delta x in Greek, in Latin, it'll be dx, okay? So this is delta x or width. So again, I've got height times width. That gives me area of a rectangle. Now I'm going to sum up all of the rectangles from where to where. Guess what? From A to B. Okay? So I'm going to do length, height times width, one rectangle, sum them all up from A to B. So that's what that notation is. Isn't that clever? Okay, so the way I read this is the integral from A to B of f of x dx. Okay? So let's do an example. Suppose I got this. I've got, I don't know, some whatever, and my region is from 2 to 4, and I want to find the area here Okay, and suppose this is y equals x squared. Okay, the way I write it is, I want to sum up, okay, all of the rectangles. So what are the rectangles? How do I get the rectangles? What's the height of the rectangle? If that function is y equals x squared, what's the height of the rectangle? X squared. The width is delta x dx. And I'm going from 2 to 4. So that collection of symbols is that shaded area. Okay? All right. So that's a definite integral. It's basically just a sum of the rectangles. Okay? And I always tell people this, like when I'm teaching calculus and when they start doing integrals, don't ever forget how we got this. We came here by manually drawing rectangles, taking the area of each one and then adding them up. Now we have a mechanism that lets us do that. So what this does is draws a series of rectangles, adds their areas. Okay? All right. So definition. Okay, so what's area under the curve? If y is non-negative and integrable over a closed interval, so basically if you can take an integral, then the area under the curve y equals f of x from a to b is the integral from a to b. So that's exactly what that just told us. Okay, so the integral is the area. Okay, so all right, so let's take a look here. The area under the curve, f of x equals root x, on the interval 0 to 4, is represented by the integral this. Okay? So, I have a curve, f of x equals root x, and from 0 to 4, if I want to find the area of that, instead of sitting there and drawing rectangles, I could just do this. So, so let's use the graphing calculator to evaluate the area under this from 0 to 4. And you know what? I have here, oh, I forgot to switch this up for the inspires. Okay, hang on. How many? Oh, you guys don't. Yeah, that's why I did it. Okay. We're good then. Okay, so let's do the 84. Huh? Huh? Yeah, because my students take, like, half my classes use the 84s. And, well, I guess no, only you guys use the 84 now. Everybody else has the Inspire. Yeah, because we're phasing them out. So next year I won't need this anymore. Okay, so here, all right, in f of x, here, we're gonna, we put in the value, so root x. Okay, and when you graph, basically, right, that's what it looks like, right? That's root x. Okay, so now, we're gonna do second calc or second trace. And here you're gonna find number 7, you're gonna use the integral. And lower limit, 0. Upper limit, 4. Enter. Oh my goodness. There it is. So what you are doing, splitting it up into rectangles, finding the area, adding them up. There it is.
Can you show us?
There I am. Okay. Now, sometimes it's like sometimes you want to see the graph, blah blah blah. Sometimes it's not necessary for you to to know what the graph looks like. So if you're in the home screen, right? So if you quit, and if you're in the home screen, you press math, and then here the 9th one here, if I just go down a little bit, is function integrate, right? So you take that, and most of you have this pretty little symbol now. If you don't, I'll tell you how to do it. Hang on. If you don't, I'll show you how to do it. So you put in, okay, so this is going to go from 0 to 4. And it's going to be root x dx. So here, you know where the x is. You don't do, well, let me see. I think you can do the x there. Yeah, you can. Never mind. So enter. There you have it. Boom. Okay? It takes a while, huh? Okay. So, and let's not worry about about method 3 for now. If your calculator doesn't have the pretty little print, here's what you do. In here, listen, this is the syntax, this is the logic. So look, you put in the function with respect to the variable, so x, all right, that's the variable, x, and x is, you could either use like you could use the same x here. Oh, comma is above the 7. Comma is its own button, it's above the 7, comma, and then you do the interval 0, comma 2. Please do it, press enter, make sure it works, and just, I'm 99.999% sure that this is the syntax.
No, I got 1.8. I got 1.8.
Oh wait, it was 0 to 4. No wonder, yeah, and of course you would get about half the area from 0 to 2. Okay, 0 to 4. Okay, I'll be over in a minute. Correct, it was 5.333. Yeah? Okay. So, so just remember that this is the lower bound and this is the upper bound. And I need to revise this next year if I'm teaching this again for TI Inspires. So funny thing, I found a good, all right, here it says evaluate the integral, okay? What does the term evaluate mean? Find the numerical answer, okay? So find a numerical answer. Okay, so sometimes it'll say, set up but do not evaluate, blah, blah, blah. So evaluate means, Okay, now it says evaluate the integral using area. Okay, so we have to use actual areas here. So here's what we mean by this, okay? What is this an equation of? A semicircle, way to go. Radius of 2, good. So there, right? That's a pretty good semicircle. So basically I need to find the area here, okay? Now, so we need to find the area under this curve. Okay, so area, okay, is another way of saying area is saying find this. From -2 to 2, 4 minus x squared dx. So here it is. This is one of my, this is one of the, like a bulletin board problem. Like if you were walking down the street, right, and you saw this on a billboard, right? Like if I was walking down the street and I just saw just this, without even the A. If I just saw this on a billboard, I'd be like, oh, somebody wants to find the area under 4 minus x squared from -2 to 2. That's what that means to me, okay? So, how would I find the area here? This is a semicircle, right? The area, no, listen, no calculator. The area is half pi r squared, right? So, this is equal to half pi 2 squared. So this is equal to 2 pi. So, very important concept here. Listen, if you are asked to evaluate an integral using area, I'm going to be looking for area formulas from geometry. So you will be given shapes like a rectangle, you know, a semicircle, a triangle, whatever. And I want you guys to be using area formulas. Half base times height, pi r squared, you know, whatever else it could be. Because this is reinforcing the concept that you know that this means area, in the traditional sense that we know it. Okay? All right. So that's 2 pi. So now, what if, okay, y was negative 4 minus x squared? What would that look like? That would look like it would have the same shape, but where? Below, from negative 2 to 2, and so on. Okay? So this integral would look pretty much the same, except with a minus sign inside, right? Okay? And now look, you could actually, you know, write it this way, or you could take the negative out and write it this way. So now, if you just compare this to that, what's different? There is a negative outside. So now, if I ignore the negative here, now what's different? Nothing. So here, this is equal to, there is a negative here, negative, and then what was all this? What did all that give me? 2 pi. So then, if my function was the same thing but underneath, what would I get for area? Negative value. So now, what does that tell us? Just like velocity, right? The sign tells you direction. It's the same thing with an integral and an area. A positive value for area means the area, it's above the x-axis. A negative value for area means the area is below the x-axis. Okay? All right, so area equals negative f of x dx when the function is at, you know, it's less than or equal to 0. Okay? So when graph is below x-axis, area is negative. Okay? And then so people ask all the time, what does it mean? Like if you can't have a negative distance, right, then what is it, how can you have negative area? And to think of it, you know, if you want to think of it as, you know, like if you have, let's say, like a hill, right, with a certain like area or volume. Now if you have like a hole in the ground with the same area or volume, like surface area or volume, that's what we're talking about. Okay? So it's like missing area almost. Okay? All right. So here, what, this one? Well, it's negative 2 pi is good enough because pi is a number and 2 is a number. So evaluate doesn't mean to get a decimal answer necessarily, just a numerical answer. Yeah. Yeah, 2 pi is fine. Yeah. Okay. Now, what are the chances that our graphs are only above the x-axis or only below the x-axis? Very, very little, right? Most of the time, a graph will fluctuate, you know, below and above the x-axis. If that happens, and, you know, of course it always does, so for any old function, you know, if it's allowed to go above and below the x-axis, then the way you find that, what does this symbol mean again? What all these mean? The area, there you go. Then this is the area above the x-axis minus the area below the x-axis. Okay. Okay, so let's do this one. So evaluate the integral of this. So basically, I want to find this, meaning I want to find the area here. Okay, this is f of x dx, and I want to find the area. Okay, look at what I have here. Triangle, triangle, triangle. So many triangles everywhere. Okay, so it says using area. So what I do is I split it up into triangles of which I can find the area. Best case scenario, right triangles. So here, I'm going to split it up. Okay, so here, the area of this one is half times 2 times 2. So area is 2. So now, this entire region is above the x-axis, so the area there is positive. This entire region is below the x-axis, so the area is negative. Yeah. Oh, you know what? Yeah. I don't know why I was trying to do two different ones. Yeah. Let's just do the one rectangle. Yeah, I don't know why we would split it up. So the entire base here is 3. So half times base times height. I was going to do 2. So taking the entire triangle, it's 3. So here, if I wanted to take the entire triangle, area is half times, again, this is 1, 2, 3, and the height is 2. But this time it's negative, right? So the total area, so from negative 3 to 3, f of x dx is equal to positive 3, and then minus the other 3, 0. So this has an area of 0 because the area on top just cancels with the area on the bottom. Okay? Huh? No, it's just positive 3 and then negative 3. So the area here is positive. Okay, so here it is. It's like this. The area under this is 3, right? So, but it's positive 3 here and negative 3 here, and then you just add them. Because it's the, yeah. Or, right. Right, because technically the absolute value of this area is 3. So you do the top minus the bottom. So 3 minus 3. Okay, now look. I'll stop here. This is the homework that's going to be due. I have it on Haiku that it's due on Wednesday. Do as much as you can, because I haven't finished it. You know, it's fine if you leave it for Thursday. However, on Thursday you also have a quiz, so it's really a good idea to start getting your practice before then. Okay?